So I went even simpler on my my little sample token protocol here, and I'm going to show why in just a second. But so just to kind of recap from where I was earlier, the same simple little token protocol. An output starts with the shrug as a push, and then in the case of a deploy, the next field is an op false. In the case of any other spend of a token, this is the out point where the deploy happened. Then we have an op2 drop that just drops those things off the stack. And I've decided that mint flag that I had last time around for kind of the admin mode is just going to be used by an op false in the amount. We never need to have an output of 0 of the token. And so I figured just use that as the flag to simplify things even more. So let's make sure I got my docs right here. So to deploy a fixed supply, I would go shrug, false because it's deploy, 2 drop, and then I'd put my supply. These values are all Bitcoin encoded numbers. That's kind of what I'm working with right now. Keep kind of going back and forth between UNT64, but I think since Bitcoin gives us big numbers, we might as well just, and it gives it natively, we might as well just use Bitcoin numbers. I am probably going to have to put a limit on the size, but it can be something astronomical. And then a drop, and that's it. So transfer, nothing's really changed there. The only thing that's changed is token deploy outputs, and then the amount of the outputs. Yeah. So here's why I've been kind of playing with this whole idea. So I'm working on kind of solving the back to Genesis problem. And back to Genesis, to kind of summarize what that is, you can have very, very complex rules within a locking script, such that it can only be unlocked if, it can analyze all sorts of aspects of the transaction that it's being spent. But there's no way within that transaction and the scope that that transaction has to be able to validate that the input that's being spent into it is an authoritative one, that it doesn't know where it came from. It didn't know that it's, so if I've got a token and I spend the token input, it can validate that it looks like there's that token in there, but it doesn't know if it actually was spent through the proper chain of transactions to be the valid one. And so whenever you hear back to Genesis, that's what that means, is a UTXO only has in it really kind of its own state, and or at least the state of the transaction that it's in or that it's spent in. But been playing around with this idea of a stateful contract, a UTXO based contract that can over multiple iterations, and it can basically validate the transactions and the token in line here. So this is not fully working yet here, but I have this. So this is a back to Genesis market is what I'm calling this contract. And so kind of the key of both how BSB21 and how this Shrugger token here is working is that, again, the token gets identified by whatever outpoint on the chain it appears in. And so that outpoint is what becomes the token ID for that token. that type of token, that individual instance of a fungible token set. So all we really need to do to validate these things is, one, make sure that the token rules are being followed in the transactions. And two, we need to make sure that those transactions that we're receiving actually occurred on the blockchain. And that's where our caveats of this whole solution comes down to. But I'm going to go through the details of it first, and I'm going to skip over some things and whatever. But okay, so first of all, we've got some constants. We'll get to those later. This is not implemented yet, so we're going to comment that out. Okay, so this contract would be me locking up one BSV in this contract and saying, I will give this one BSV for 75, name your token. Let's come up with a test. We'll call them, I don't care. I don't have good names. I'm not good at naming stuff. We've got a token. And so I'm basically saying I will pay one BSV for 75 of this token. So we keep track of what the token ID is, the pay output. That's essentially where I want to get paid my my 75 test token. So this is the actual output script itself that contains the tokens and where they need to get locked up, or what is the locking script that I will consider this having been, I guess that's what determines that this sale actually goes through, is if I get paid that script, that amount of money, or that amount of BSV, or whatever else outputs are in, whatever other requirements are on there, that's what causes this to unlock. So this token ID and this amount are actually extracted from the pay output script. So then we've got the price that I'm paying. This is a state thing. We'll get into that later. We'll get into this bond stuff later. So essentially, this is just like the ordinal lock contract for ordinals. And I'm just using this as a sample concept to see if I can do the whole validation piece. So I've got a class that mimics my shrug token, which really only has two properties: token ID and amount. But I also want to be able to tell if this script that I'm trying to create this instance from actually is a token or not, is a shrug token. And so here's the code to just parse out from a script this shrug token. So we start with kind of some empty values. And this is really just parsing the script to make sure it is well formed. It's got the op drops in the right spots. Oh, actually. Oh, no, I finished that. So yeah, this is just parsing to make sure that the output we're looking at complies with these rules over here. So let's go back over to our. So when we construct this thing, we pass in the pay output. We pass in our price. Again, that's the price we're paying. Verbiage could totally be updated on this stuff. And the deploy script, which is, so this, as for part of the validation purposes, I actually need the script where this where this token ID was deployed. And I need that for the validation purposes. So that gets put in there as well. Where am I? What am I doing? Oh, I'm parsing that. So then I'm parsing out the pay output, getting from that the token ID that I want to receive. I'm getting the amount of that token that I'm wanting to receive, and I'm saving those in the contract. I'm not going to make that stateful for now. We parse the deploy script. Okay. So this is just kind of setting up. I will go through this other bonding stuff and valid hash out or valid outpoint hash stuff later. But the idea here is, okay, when I have a transaction that is spending tokens as inputs, those tokens need to have come from the outputs of a previous transaction that also was a valid, I mean, obviously this is all back till we get to the point of that deploy. So conversely, if I get proofs provided that show from that genesis that got put in the constructor here, from there, if we can get all the proofs that walk forward to the actual transaction we're in right now that we're trying to spend, and we use that as a mechanism for unlocking this contract, that should be essentially FPV validation. That is what that is validating the Merkle roots or the Merkle proofs and the script or the transactions themselves. And then knowing then that those outputs are good so that we can do the next transaction going against outputs that we've already validated, working our way forward till the point where what we have proven are the actual assets that we're going to spend to pay for or to fulfill this order, essentially. So there's some caveats with all that, and I'll get to those caveats later. But essentially, what we need to do here is this is a stateful contract that we're going to call many, many times. One time for every output that we are proving. And so we've committed the deploy script, and so kind of the next script that comes after that. It was maybe that deploy was a mint, and then it minted some tokens to, let's go to the simple case first. It minted some tokens to you. And so what we're going to need to prove is the steps from, I keep looking at my picture of me instead of the camera. What we're going to need to prove is that we're going to need to prove the transaction where the deploy minted you tokens. I guess that's only one transaction. Deployment. We got a mint. Yeah, that's only one step. That's okay. We'll start with the one step. So what we're going to pass into this validate transaction is our full raw transaction. We need which output we are going to be validating. If you happen to have a transaction where you have two of the outputs, you're proving both of them. Well, right now you're going to have to call the contract one time for each of those to establish those. We have the block header of the block where this transaction was mined. And we have the Merkle proof of that transaction in that block. And then we have two other things here, and this is where we're going to start. So this validated outputs is what are the out points that we have already validated to this point of running the script. And I'm storing that as a byte string because this actually made the compile size a lot smaller. So they do have hashed maps in Scrypt, but I'm not totally positive how it works under the covers. And so that kind of, and I know that it makes things big, or at least it appears to. I could be using it wrong, but anyways. So this is just essentially a big old buffer that has got a bunch of out points that I have already validated. Then we have input indexes. So this is saying that these are the inputs. I don't want to say that. These are the inputs in this transaction that the inputs in this transaction that have tokens that we have already that have tokens that are in this validated outputs. So this is all the validated outputs the contract is keeping track of totally. And this is which of these outputs are being spent in this transaction and in which position. That was a long way to say that, but and I'm kind of using encoding here where we put -1 if an input is not, so say it's a BSV input or something, and we don't need to validate it. It has nothing to do with the validity of the token. Doesn't care. It doesn't affect what actually happened in that transaction. So, and then we do have to set limits on this. So Bitcoin script, you can't just kind of loop until something. You have to basically give it a max number of iterations, or at least I should say Scrypt. There are some voodoo black magic where I'm not even going to get into that. I totally don't understand anything other than just when you have code in a script, it certainly can't be dynamic. It's going to, you can only execute part of them. You could have a loop that's got the same code 10 times and you only execute the first 4 because that is all that matches your logic, but you have to have a max size. And for whatever size that is, that code is going to get copied. Unrolling the loop is copying the code over and over and over again. So we've got to set some realistic expectations of how big these transactions can be. So that's where some of these constants come in. So I've got, what did I set it at right now? Okay, so I've got limits that says there can be 10 inputs and 10 outputs. I don't use that anymore. So that means the code that's in here is going to be looped over 10 times, and so I need to have my array of data be essentially 10 long, and so that's what this is. This is setting how many elements will be in that static type. Okay, so all I'm actually, let me go back up to this into my state variables. So I am keeping in state, like in the contract itself, just a hash of my validated outputs. So, I mean, it's kind of actually whether you store data in the contract itself, in the UTXO itself as part of the locking script is state data, or whether you pass it in the inputs. Like from a size of the transaction standpoint, it doesn't really make any difference which way you go. But just from a size of the UTXO set standpoint, I can keep these UTXOs considerably smaller by just keeping a hash of the valid out points rather than keeping all of them in my UTXO. again, it really, as far as transaction size, it doesn't make a difference. But as far as how big the UTXOs are, it makes a big difference. Okay. Let me actually just close. We already talked about that. That doesn't matter, and we're not looking at that right now. Okay. So first thing we're doing here is we're hashing the validated outputs that are passed in, making sure that that does equal the hash that we've stored in our state. Then I generate a transaction ID by hashing our raw TX that comes in. And this is actually Scrypt has this blockchain library in their GitHub that already did all the Merkle validation and block header validation and everything for us. Oh, there's another constant, by the way. So as blocks get bigger and bigger and bigger, your Merkle trees can get deeper and deeper and deeper. And now Merkle trees scale very, very well, but still the same type of logic of, because I'm going to have to loop over a Merkle proof, the contract needs to have kind of hard coded into it what is the deepest Merkle tree I care about, or that I can process. So if the chain gets bigger than what that can support, this couldn't validate it anymore. So what do I have here? So I have a max tree depth of 32. So that's like when blocks, that'll be good until blocks can be over 4 billion transactions. And at that point, now again, these outputs are already out there. So if the chain gets to be that big, it can no longer validate that. It can no longer validate those transactions. So now, if most of these contracts probably won't be open for, like this one right here, this would be like it's on a market. They put an order out, a couple days later they close it. It's not like we're talking months or year. I mean, it could, but likely the use cases would be they'd close down pretty quick. Or yeah, either a purchase would be made or the lister would cancel it. All right, so then that's so they also, Scrypt also has a transaction parser library. I didn't need nearly anything that's in there, and there was a couple optimizations I could make. So I just kind of made my own little copy of theirs, or mine based on theirs. So we parse the transaction. So essentially we are now reading the input count from the transaction. We are asserting that the input count is less than or equal to our max inputs. That just, we couldn't process it, so we're not even going to try. Or actually, I shouldn't say that. It's not that we can't process it, so we're not even going to try. It's we cannot validate the tokens in this transaction. So that's not a transaction that this contract can validate. We're going to keep track of how many tokens came in the inputs. This has mint is for validation purposes. We'll get there. Okay. So I'm looking through I to max inputs. So that's the other thing with how you have to do conditional looping in Scrypt. So first of all, your to value has to be a constant, or a constant. And you don't really have continues or breaks. You have to do that flow control through nested ifs, which is fine. It's just so basically, I read in how many inputs this transaction has. If I'm less than that, because this is a zero-based index, this is a 1, so I want to be less than. Okay, then I look at the input indexes. So this is what the user passed in that said these are the inputs that that I've that I'm spending there that have been validated that you need to validate. So, and -1 is passed if we're skipping that one, or if that's not related to the token at all. Okay, so then I read in the out point that's being spent in this input. Okay, so what is being passed in this array? So the index of the array is the index of the inputs. The value is what, which indexed output in this validated outputs correlates with that input of the transaction. So let's see here. And each one of these values in these validated outputs is 44 bytes long. And actually, let's go into that encoding right now. So what is stored in each one of those 44 bytes is, oops. Yeah, this is what gets hashed. So what is in there is essentially the token ID. So that's 36 bytes. That's a transaction ID and an output index. Plus, I'm storing the amount of tokens that have been validated in that output. And I'm just squishing those together. So that is 44 bytes. 36 plus 8. Let's see here. So I read the out point off of that value, and then I assert that the out point that is being spent by my input is that same one. Then from there, I parse out the token amount from what I've got saved in my validated outputs. And then that change I said earlier is if that amount is 0, that means that this is a mint or a admin or super or whatever we call this token. Otherwise, I add that token amount to how many tokens are in the inputs of this transaction. Then we kind of do the same thing with outputs. We keep track of how many tokens are going out. We read how many outputs there are in the transaction. We make sure that that's not more than our max. We loop through the outputs. We parse a token out of the output. If it is a token, and this is a part actually I have not finished this yet. So if it is a token, then if that token's amount is 0, that means we are creating a new mint. So in order to be valid, we have to have spent a mint. There has to be a mint that was spent. So this was looking at our inputs and identifying that there is a mint there. And I add the tokens out. Actually, one thing I did not do here, I need to say if token.tokenID, equals this token ID. So it's possible that a transaction could have more than one token in it. And I need to make sure I'm only looking at the tokens we care about. Okay, actually, yeah, so this is the validation part. So okay. So one other thing I need to do here, because back in our, we're supposed to be specifying which of these outputs we're validating the whole transaction. You have to validate the whole transaction to validate any one output. But we are only marking one of these as validated. So we're going to say I don't want to do that. Well, yeah, I do. So if actually that needs to be in here as well. This needs to be a big int. Thank you, but no thank you, Copilot. Oh, actually, I skipped one step up here. As I was going through the inputs, I find that the person pointed out that that they're going to be spending and that are essential are inputs of this transaction. Those also get removed from our list of validated outputs. So once it's spent, we don't need to keep track of it anymore because we've already validated something that spent that token, and so therefore we don't need to save it anymore. So as I'm going through the inputs, I'm pulling out the one that we spent, and then as I'm going through the outputs, I'm saving what is output? No. So then I need to, where do I have that? I need the out point and the amount. So TXID plus yes plus utils ULE unsigned token. Yes. Okay. So I'm just appending that on the end. And then finally, now I haven't actually, this needs to have some signing and I'll get to more stuff than that. But essentially, one call to this transaction or to this function will update the validated outputs one transaction at a time. And each of these transactions has multiple inputs and multiple outpoints. Every one of the inputs has to have already been validated. So you have to walk from oldest to newest. So every input that you need to validate, you need to have already validated that transaction before it. And so that's where we're starting at the back and working our way forward. So let's talk about the bonding a little bit. So this contract again is I am putting out a buy order. It says, here's one BSV. I want to buy 75 of token X. But somebody who could be anybody out there has the opportunity to buy this thing. And they could, because they're submitting, they could make fake block headers. They could do all sorts of stuff. They could corrupt the state of this contract. Because it isn't really until we're done with the process that we have their actual assets on the line, that their whole validation process goes to unlock, that we can actually kind of finalize the deal. So within that time period, that one person kind of has to have exclusive access to spend this contract. And that's fine, but they need to, like, they're basically taking it off the market. And so they have to be able to complete that transaction, or else they could just kind of leave this order in a kind of bad state. And even if, I mean, we do have methodology for the person who put the offer out there, they can cancel that. They can say no. So, but if someone's in the process of buying and they've already spent a bunch of transaction fees to prove this, you don't want to let that seller just, or the buyer just pull the plug at that point. So we need some way to kind of equal out the incentives for this whole process to play through. And I believe Ty had come up with this idea for his Bitcoin CPU project. But it's basically, when I go to start buying this or fulfilling this order, I actually have to post a bond. And if I complete the process successfully and I provide all the proof and I complete the order, I get that bond back, as well as the money that's locked up in this contract, and the buyer of my tokens will have gotten fulfilled their tokens. But if I just want to lock up this contract and dick around the seller, by posting this bond, that seller is going to get recuperated for their item being pulled off the market for a while. And that's another one of our constants up here, is what is the amount of the bond. Now, right now it's 1,000 Satoshis, which is not going to be worth anything. It's just a placeholder. And then how many blocks is that bond locked up for? So I have 6, so an hour right now is kind of what that's saying. So if I start proving this transaction, I bet if I complete it in an hour, everyone's happy. I got my money. They got their tokens. But if I don't prove it in that amount of time, then they can just claim my bond and relist their tokens. So we've got a method here to post bond. So how that 6 block time works is the person posting bond, actually, yeah. So they kind of set their start time. Actually, I'm not sure I've got my logic right here, but I'll talk through the concept before, not necessarily the implementation. But essentially, only one person can have paid bond at a time. Again, that line I think is wrong. They pass in the pub key of essentially who they are, or what key needs to use in order to sign off on their transactions. And then the other output here, or the other input into this transaction, is a list of trailing outputs that are going to be other than just this one output itself. I've been tending to do this a lot in my script programming lately. It means your contracts are very flexible to be used in many different types of transactions, and other assets could go along with them in the same transaction, and it just gives you a lot of flexibility. Oh, I commented that out. So the buyer, which is again the person putting up this. Oh, I didn't actually set that. Well, whatever. We'll get around to it. The person who put this contract out can cancel it, but they can only cancel it if it isn't bonded or it is bonded, but the height has passed. The bond, yeah. The height they bonded at plus the number of blocks less than the current lock time of this transaction. So that's where I've got right now. So the caveats I do want to talk about on this are this is only as good, and this is this little to-do right here. So this script can validate block headers and it can validate Merkle proofs, but it can't validate that the block headers that are being passed into it actually existed on the chain. And there is still proof of work in those block headers. So this contract is only as good as it is economically costly to counterfeit a block that this will accept. And so this is kind of the one fidgety piece that, I mean, if this were running on BTC, so here's what I actually have implemented right here is, actually that one's not going to work. So essentially there's a minimum difficulty that this needs to be built with. And there is risk involved in that difficulty. So what that means is a regular old valid Bitcoin block, we need to set this difficulty to the lowest hash rate that we are that the chain will, I mean, the assumption is hash rate will generally keep going up. So what you're basically locking in is this is the minimum amount of proof of work that I need on a block header for me to trust that it's a real block header. Problem with that is BSV right now is, I mean, each block gives you 3.5 BSV or so. I mean, with the fees and the subsidy. So the assumption is a block costs $175 to mine, which means this is really only good for about probably $150 worth of value to be locked in it. Now, as hash power goes up, especially if the hash disparity changes, like if this were running on BTC, you could set that at a fairly low threshold. Every block will always fulfill it, and it's still way more energy than anyone's going to put in to try and steal from a contract like this. So that's the big stipulation here, is we don't actually know that the block headers we're getting are from the chain the actual chain tip is on. But we do have the ability to set a minimum difficulty. And the cheapest way to do that is always to use the valid block headers that other people have already mined. So that's kind of the one big gotcha, that right now this can do full back to Genesis validation, and I'm going to work on a test for that to illustrate that. But it's not really for high value assets at all. But if you're doing little rinky-dink stuff and you want to be able to validate that tokens are legit, it should work for that. I think that's going to be it for tonight. I did want to share this and get this out there. I'm going to keep working on it some over the holidays, but I also have family stuff. So, yeah. Good night, everyone. Merry Christmas and all that. Bye-bye.